Hey guys, in this video we're going to talk about Chapter 16, Section 3, Triple Integrals. So last time we looked at double integrals, and we talked about finding volumes bounded by a flat region on the xy plane and a surface. So for example, we looked at something like this. We had some kind of surface, some z equals a function of x and y, and we considered the volume bounded by the xy plane and that surface. And we looked at that over rectangles. I think we did one with a triangle as the domain in the xy plane. And today we're going to bump it up a dimension because that's what we do when we learn things. We keep going up and up and up. And what we're going to do in this lecture is we're going to talk about finding volumes in the traditional sense of the word volume, but we're also going to talk about finding quote-unquote volumes, meaning we're finding areas under 4D surfaces, okay, or volumes under 4D surfaces, which we can't visualize 4D, right? It's not really in our realm of reality to visualize such a thing, but we can still do calculus nevertheless. Okay. All right, so let's talk about what we've covered so far in calculus. In Calc 1, we had a function in one independent variable, and when we integrated it, we looked at the area that was made with the curve, f of x, and the x-axis. And the axis that we traveled along was the x-axis, right? And that's where we got our dx from. That was the width of the rectangle that we were considering, the very small width. So we integrated just along the x-axis when we have a problem like this in single variable calculus. Now last week we talked about integrating on a region. Okay, so this, the x, we're integrating along the x and the y axis this time. Sometimes we integrate with respect to x first and hold y fixed. And sometimes we can switch the order and integrate with respect to y first and hold x fixed. But the way to think about this dx times dy is like a length and a width of a rectangle, right? If you multiply the length and the width of a rectangle, you're going to get the area of that rectangle. And so we could represent that as dA if we wanted to. So yeah, we integrate along the x and the y axis last time. Now we're bumping it up a dimension. Now we're going to integrate along the x, y, and z axis. Okay, so when we do that, we have a triple integral. Okay, and we're going to be integrating along some three-dimensional region, right? It's not going to be on the xy plane anymore necessarily. It could be something in 3D. Okay, so I wrote B for box. You can think of it as a 3D thing that we're integrating on. Whereas up here, we can think of this as like a region just on the xy plane. And notice that this time we have a dx, a dy, and a dz. And we can think of these as dimensions of a very, very small box, right? So if we have some very small box, we can consider the change in x, the change in y, and the change in z. So the change in z could be the height, so this would be dz. The change in x could be parallel to the x-axis, so dx could be this guy right here. dz we can do in green, I guess. And then dy could be this guy right here. So this is a dimensions of a box, right? And to find the volume of a rectangular prism or a box, we just multiply the length times the width times the height. So remember the volume of a box is just length times width times height. So we can see here that the change in volume, or the volume of this box, is going to be, well, dx times dy times dz, because that's the dimension of our infinitely small box. Okay, so anyway, we're going to be integrating along the x, y, and z axis here, and instead of writing dx, dy, dz, I'm going to replace that with the change in volume, dv. Okay, so how does this work in practice? Well, I'm going to do a pretty simple example to show you guys how we can find the volume of a figure using triple integrals. Now, you might be saying, well, why the heck am I going to use a triple integral to find the volume of a box? Hello, geometry. Why don't we just use the basic formula, length times width times height? Well, it's just to show you, that the calculus does work, okay? And we're going to apply that calculus to more difficult shapes, right? We're not going to just have boxes here. We're going to have lots of different scenarios. Okay, so here's the idea. So here's our very small box right here. So we're going to integrate along the y-axis, right? We're going to integrate along the x-axis. We're going to integrate along the z-axis and consider the change in volume. So here are the dimensions of our box. So we're being told that the box has a height of 10, right? It says z ranges from 0 to 10. So here's 0, here's 10, right? That's the height of the box. X is going to range from 0 to 3. So this is 3 right here. So that's our dimension 3. And maybe I'll actually color that in. That's our dimension of 10. And then Y is going to range from 0 to 15. Okay, so we want to set up a triple integral to integrate this region, along this region. So let's just set up our integrals, and we're gonna be integrating 1 since we don't have a function defined. And it doesn't matter what your order of integration is going to be. So I'm going to do dz, dy, dx. So I'm going to integrate with respect to z first, then I'm going to integrate with respect to y, and finally with respect to x. But it doesn't matter how you order them, as long as your bounds are in the appropriate spots up here. Okay, so my bounds for z is going to go on the innermost integral right here, and z is going from 0 to 10, so that's going to go there. Next comes y, so that's my middle, that's going to go from 0 to 15. And finally x is going to go from 0 to 3. Alright, so there's my integral. So let me go ahead and integrate this thing with respect to z first. Now, this is pretty easy. It's just 1. So with respect to z, this is going to just be z. Right? And we're going from 0 to 10. And we still have all of this other stuff on the outside. dy, dx, 0 to 15, and 0 to 3. So I'm just integrating with respect to z right now. Okay, so this is just going to be 10 minus 0, which is 10. So if I rewrite this, I get 0 to 3, 0 to 15, and then I have 10 dy dx. Alright, so I integrated with respect to z. Now let's integrate with respect to y. So if I integrate 10 with respect to y, it's just 10y. And my bounds are going from 0 to 15, and I still have this other stuff on the outside. Okay. So if I plug in 15 for y, I get 150 dx from 0 to 3. And finally, I'll integrate this guy with respect to x. So that's just going to be 150x, and I'm going from 0 to 3. So that's just 150 times 3, which is 450. Alright, so that's my volume. And the volume of that box. And it makes sense, right? Because if you check without calculus, which is the way that everyone should do this, but I'm just showing you guys that the calculus works. If you check this thing, you just take the volume. So you take the volume by multiplying the dimensions. So you have 10 times 3, and then that green guy was 15. Sorry, I didn't label that, but that was 15. Yeah, so V is equal to 30 times 15, which is indeed 450. And we're not given units, but this is going to be units cubed. Okay, so here is our definition for a triple integral as an iterated integral. So this is where we're integrating on, so B for box, but it doesn't have to be a box. It could be any region or three-dimensional object. And then we have our function f times dv, change in volume. And then we have our integrals with our bounds here. And here we have dx, dy, dz. So integrate with respect to x first. This a to b corresponds to the x values. The middle one is dy, and the last one is dz. But an important note is that you can change the order of integration around if you want. You don't have to integrate with respect to x first, and then y, and then z. You just have to make sure that your bounds are consistent with your dx, dy, and dz's. So before we start actually getting into like the meat of the material, which is setting up our own bounds for integrals, let's practice just evaluating some integrals, some triple integrals with the bounds given. So here it looks like we're integrating with respect to x first. So this guy right here is going to correspond to x. So let's just say this is x equals 0 to x equals y minus z. The second one corresponds to y. So we have in the middle, we have from y equals 0 to y equals z squared. And the last one's going to correspond to z. We have z equals 0 to z equals 2. So let's go ahead and integrate this function with respect to x first. Now remember, when we do that, everything else that doesn't involve an x is understood to be constant. So when we integrate with this guy with respect to x, we get 2x squared over 2 minus xy. Remember, minus y is understood to be a constant. And our bounds, we're going from x equals 0 to x equals y minus z. So I'm going to plug in y minus z in for x. These clear right here. So I get y minus z squared minus, and then again I have y minus z. And maybe I'll put the y in front. This y right there, I'll just move to the front. Alright, so then I still have my other two integrals. I'm going from z equals 0 to z equals 2, and then right before that I'm going from y equals 0 to y equals z squared. Okay. Alright, so I took care of that first one, so let me go ahead and put the dy dz there. Now I'm going to integrate with respect to y, but before I do that, I'm going to go ahead and distribute what I have, what I have first to do that. Okay, so y minus z squared, let's see what that gives me. And then the minus y times y minus z is minus y squared plus yz. Okay, so this is going to give me y squared minus yz is minus 2yz plus z squared minus y squared plus yz. Okay. Alright, I do have these like terms I can get rid of right there. And I have negative 2yz plus 1yz is negative 1yz. So this becomes z squared minus 1 yz. And I'm going from y equals 0, I haven't integrated yet, to y equals z squared. And then from z equals 0 to z equals 2. Alright, so let's go ahead and integrate this guy with respect to y, meaning that everything that doesn't involve a y is understood to be constant, such as this z squared. So when I integrate that guy with respect to y, it's just yz squared. And then this guy with respect to y is minus y squared z over 2. And I'm going from y equals 0 to y equals z squared. So plugging in my y equals z squared, I get z squared times z squared minus z squared squared z over 2. And then minus, well, I'm going to plug in 0 for the y's. That's going to all go to 0. So I don't really have to worry about that. Okay, so this becomes z to the 4th minus, okay, so this is z to the 4th times z, which is z to the 5th. So that's z to the 5th over 2. And I'm going from z equals 0 to z equals 2 dz. So right now I'm trying to integrate this, and that will be my last step. Okay, so I'm integrating with respect to z. Now let's move this. I guess I can go down a little bit more. Cool. All right, let's go ahead and integrate this. So z to the 4th is z to the 5th over 5. Z minus z to the 5th over 2 is minus z to the 6th over 2 times 6 is 12. And I'm going from z equals 0 to z equals 2. Okay, if I plug in 2 for z, I get, let's see, 2 to the 5th is 32 over 5 minus 2 to the 6 over 12. And if I plug in z equals 0, it's just going to clear, so I don't really have to worry about those guys. Let's see. So 2 to the 6th over 12. All right, so I have 32 over 5 minus 2 to the 6 divided by 12. And I'm getting 16 over 15. So that is my answer there. That is how I can evaluate this triple integral. All right, let's do another example. So notice, guys, that this function right here, we cannot visualize it, right? Because yes, it involves x, y, and z, but it's saying that z is also an independent variable. So this is like a 4-dimensional function. We can't really visualize this. However, the calculus, as I said, works out the same. So we're trying to integrate this function on a rectangular box. Okay, so B is the rectangular box given by these dimensions. Okay, so we need to go ahead and set up our integral, set up our bounds. Now the dv is going to be d dz, dy, dx in whichever order you would like. Okay, I like to do the z first just out of habit, but it really doesn't matter. So let's go ahead and set up our integral, our integrals. So we have x, y, z squared. Okay, so what am I going to do first? Well, I'm going to do z first just because I want to. You don't have to. You could do x first, you could do y first, it doesn't matter. But I'm going to do dz, dy, dx in this order. And since z comes first, my z bounds go first. So z is going from 0 to 3. So 0 to 3. Y comes next. Y is going from -1 to 2. And finally, x is going from 0 to 1. Okay, so that is that. Now let me go ahead and integrate this. Okay, so let's see. Okay, so we're going with respect to z first. So again, this xy, imagine it as a constant number like 4, 5, or 6. How would you integrate 6z squared? It's pretty easy, right? You just add 1 to the power and divide by whatever you get when you do that. Same thing. So when I integrate this with respect to z, it's just x, y, z to the 3 over 3. And I'm going from, and I'm actually going to maybe write this just to make it a little bit more clear. I'm going from z equals 0 to z equals 3. So I'm plugging in for z, okay? So when I do that, I get x, y, 3 to the 3rd over 3 minus, and then if I plug in z equals 0, that's going to go to 0, so let's not even worry about that. So I get 9. Yeah, 27 over 3 is 9, so I get 9xy. So I just took care of that first integral with respect to z. This is what I got. Now let's go ahead and look at the other two. So the second one, we're going from y equals -1 to y equals 2. And the outermost one, we're going from x equals 0 to x equals 1. And I'm integrating 9xy first with respect to y, then with respect to x. Alright, so with respect to y, this is going to become 9xy squared over 2. And I'm going from y equals -1 to y equals 2. Again, I'm just treating that 9x like it's a constant number. Okay, so when I do that, I get 9x 2 squared over 2 minus, I got to be careful here because my lower bound isn't 1, minus 9x -1 squared, or my lower bound isn't 0, I meant to say. Okay, so there we go. Okay, so this is going to be, let's see, 18x. Yeah. 18x minus, let's see, this is going to be, yeah, this is just going to be 9 halves x. And I believe, yeah, that's it. Okay, so then we're going from x equals 0 to x equals 1 dx. And I can combine these like terms if I want, because 18 is 36 over 2. So 36 minus 10 is 26. So minus 9 is just going to be 27 halves. So this is 27 halves x dx from x equals 0 to x equals 1. All right, let's go ahead and compute this. So let's go ahead and integrate this with respect to x. So this is going to give us 27 halves x squared over 2. Okay, so this is just 27 x squared over 4. And I'm going from 0 to 1. So if I plug in 1, I just get 27 over 4 minus 0, which is just 27 over 4. And that is my answer. Alright, find the volume of the region bounded by z equals x plus y. X is between 0 and 8, and y is between 0 and 8. And the planes x equals 0, y equals 0, and and z equals 0. Okay, so we need to set up our integral with these bounds. So again, it doesn't matter which order you do this in. I don't know why I do z first. I think you should do the quote-unquote harder one first. Because z isn't smashed between two numbers. It's smashed between a number and a function. So I would do this one first, just because it's going to make your calculations a little bit cleaner. Alright, cool. So there's z. We can do y next. It doesn't matter. And then we can do x. Okay, so, and our region, so we're, let's see. Yeah, so I'm going to just do 1 right here because I'm not given a specific function. And then I'm going to do dz first, followed by dy, followed by dx. Okay. So for z, my lower bound for z is z equals 0, right? They tell us that right there. So we're going from z equals 0. However, I'm bounded above by a function, not just a number, but a function. I'm bounded above by x plus y. No worries. That's perfectly fine. We can do that. All right, so z's taken care of. Let's do y next. So, because that's my middle. So y, I'm going from y equals 0 to y equals 8. So y equals 0 to y equals 8. And then for x, I'm going from x equals 0 to x equals 8. I can see the 0 here as well. So x equals 0 to x equals 8. So let's go ahead and do this. All right, so if I integrate 1 with respect to z, it's just z. So I have z, and my bounds are from z equals 0 to z equals x plus y. So when I plug in x plus y for z, I just get x plus y, and then minus 0, which of course is 0. So that was it. Cool, I integrated with respect to z. Now let's do y. So I'm going from y equals 0 to y equals 8. And then with x, I'm going from x equals 0 to x equals 8. And this is dy dx. Okay, so now first I need to treat x as if it's constant since I'm integrating with respect to y first. So this is going to be xy plus y squared over 2 from y equals 0 to y equals 8. Right, I just held x constant, just treated it like it was a constant and integrated with respect to y. So if I plug in 8 for y, I get 8x plus 8 squared over 2 minus, and then that whole thing is just going to go to 0 when you plug in 0 for y. Cool. All right, so that is that. Let's go ahead and do our last step, which is integrating with respect to x. Okay, so let's see. This is 64 halves, which is 32. So I'm going from x equals 0 to x equals 8. And I have 8x plus 32 dx. So when I integrate this guy, I'm going to get 8x squared over 2 plus 32x. I'm going from x equals 0 to x equals 8. Okay, so if I plug in 8 first, I get 8 times 8 squared over 2 plus 32 times 8, and then minus the whole thing's going to go to 0, so I'm not going to show that step because it's just redundant. Okay, so let's go ahead and compute this. Okay, so I'm getting 512. Okay, so that is the value of this triple integral right here, the volume of the region bounded by these surfaces. Okay, so I kind of cheated. I have the picture here, but I just want to kind of draw this out for you guys, and just so you guys can see how it matches the picture. Okay, it says describe the region of integration. We see it right here, but let's not cheat. Let's pretend that's not there. And let's go ahead and do a little sketch and use our observations to see, what's happening. Okay, so it looks like in this little problem here, it looks like I'm integrating with respect to y first. So this is saying that y is between 0 and square root of 1 minus z squared. Okay, so what does that mean? Well, that means that we can draw a little picture here, because z is acting like my independent variable here. So I have z on the horizontal axis, right, because it's like my input of the function, and y depends on z. You see that? Y depends on z. I'm integrating with respect to y. Y depends on z. Y varies from 0 to the square root of 1 minus z squared. So here, so this is y equals, by the way, so this is y equals 0 to y equals square root of 1 minus z squared. If I put in 0 for z squared, I get 1 minus 0. So if z is 0, then what's y? Well, y is going to be 1. Right? When z is 0, y is 1, so that's going to be right here. How about when z, so these are just, key points, right? The observation here is that what we're drawing is a half circle, right? Because the equation of a circle is x squared plus y squared equals r squared. So if we were to isolate y, we'd get y squared equals r squared minus x squared. Take the square root, y is equal to plus or minus r squared minus x squared. So it looks like this, right? That's what I'm trying to get at here, is that this looks like that. So it's a half circle. And so I'm just plugging in some key points here to see what the picture looks like. One of those key points is when z equals 0, y equals 1. When z is equal to negative 1, so when z is equal to negative 1, well, that's going to be 1 minus 1 is 0. So our output here, y is 0. So when z is negative 1, y is 0. This is 1. Somebody's doing donuts outside, speeding down my street. Man. Okay, so that's one other key point. And then the third one we can plug in z is 1. And so what would y be if z were 1? Well, it'd be 1 minus 1 squared is 0. So that's also going to be 0 as well. So here's the half circle here that you can see. And so we should see this picture. If this were a multiple choice question and you were to pick the right answer, well, what we're going to see is that z is varying between negative 1 and 1, and y is varying between 0 and 1, right? And that is, you have to kind of tilt your head a little bit and think of this as the axis that I drew here, right? So like this is the point here, and point here. And so that corresponds to that. So that's our y values. That's the hard part, is the function one. But the other parts aren't too bad, because this says that z varies between negative 1 and 1. And in our picture, indeed, z does vary between negative 1 and 1. Check. And then x should vary between 0 and 1. And that also checks out, because 0 is in the back here, like at the back of this figure, and here's x equals 1, so that checks out as well. So this is the region that we're integrating on. It's a 3-dimensional region. We call it B, like a box, but it's not a box. Not in the strict sense of the word box. But anyway, that's the region that we're integrating on. Okay, let's try this one. So we're going to find the volume of the region bounded by all of this stuff. You can draw it if you want. But I like to just kind of reason through this algebraically, because some of these situations you actually can't draw. Like it gets so complicated that you can't draw it. And that's how math goes. If you go along further in math, it's going to get so wild that you're not even going to know what you're doing anymore. So let's go ahead and set up these integrals. All right, so we're not given a specific function, so we're going to assume that it's 1. So we're integrating 1. And I'll put my integrals here. All right, so again, it looks like z is the more complicated one because we have that function there. So I'm going to start with z again. And so I have two bounds for z. So I'm going from x plus y is my lower bound, And maybe I'll put the z here as well. Z equals x plus y is my lower bound for z, and then my upper bound is going to be 36. Okay, so this is going to be 1 dz. Okay, so now we need to talk about x and y, because this time we don't have a rectangular region. We're just being told that x is 0, y is 0, but we're not being told like upper and lower bounds there. However, we are given z as a function of x and y. So what we can do to get our x and y bounds is we can manipulate this function and draw a picture. Okay, so what do we know? What do we know about being on the xy plane? What do we know about that? Well, we know that z is fixed. Okay, that's what we know. We know that z is fixed when we are on the x and y plane. And so here we're given this z value is 36. And so if I plug in 36 in here, now I'm just in a function of x and y. So I have 36 is equal to x plus y. Right? I'm just subbing in 36 in here so that I can draw what this looks like in the xy plane without worrying about z. Okay? Because all I have left are my xy bounds. That's all I care about. Z is done. Z is done for. So here is what I have. Now what I can do is I want to be able to sketch my region. So to do that, I can isolate y so that it's a line. And to isolate y, I can subtract x from both sides. So I get negative x plus 36. And meanwhile, x equals 0, y equals 0. So here's x equals 0. Here's y equals 0. Right? Just the horizontal line that goes to the x-axis is y equals 0, and then x equals 0 is the vertical line that goes to the y-axis. And then my line, y equals negative x plus 36, is also going to be part of that picture. So if this right here is our y-intercept of 36, it's going to have a slope of negative 1. So it's going to look something like this. Something like that. And so our region is going to be this guy right here, this little triangle. Right, it's bounded below by y equals 0, bounded above by that line. Cool. Alright, so the line is y equals negative x plus 36. That's our line there. So if I want to do y next, what's my lower bound for y? What is my lower bound for y? Well, my lower bound for y, if I'm starting at y equals 0 and I have my little arrows going up to the upper bound like this, right, my lower bound for y is just y equals 0. My upper bound, though, is this function, right? It's not just a set value, it's this function. It's going to be y equals negative x plus 36 is my upper bound for y. And then for my last bound, I can write that in terms of the constants. I don't have to write it in terms of a function. It's something called Fubini's theorem. We're not going to talk about it in this class, but just know that your last bound can be constants. It doesn't have to be a function, at least with the examples that we're going to be doing. Okay, so what's my leftmost x value? Well, that's going to be x equals 0. And what's my rightmost x value? So this is x equals 0. My rightmost x value is this guy. And what is that? Well, that is when y equals 0. And when y equals 0 in this function, I get 0 equals negative x plus 36. Solve for x. X is 36. So that's my rightmost value right there. And now I can go ahead and finally figure this out. You see what I mean? The bounds are the hardest part to figure out because you have to do all this extra scratch work. So anyway, that was dx. So let's go ahead and integrate this thing. Okay, so with respect to z, first, that's just going to be z. And I'm going from x plus y to 36. So this is going to be 36 minus x plus y. So 36 minus x minus y. And now I have x equals 0 to x equals 36. Y equals 0 to y equals negative x plus 36. And now what I'm integrating is 36 minus x minus y dy dx. Okay, so we're going to integrate with respect to y first. So anything that doesn't involve a y is a constant. It's considered a constant here. So this is going to give us 36y minus xy minus y squared over 2. And we're going from y equals 0. I don't know why I put, it looks like a 6, but it's a 0. To y equals negative x plus 36. So the 0 is nice. That's going to clear. We don't really have to put in the lower bound, but for the upper bound, we have 36 times negative x plus 36 minus x times negative x plus 36 minus negative x plus 36 squared over 2. And we can simplify this. We can go ahead and simplify this because it's just kind of a hot mess right now, to be honest. Okay, so that's going to go to negative 36x. Let's see, what's 36 squared? Big number, 1296. Okay, then I'm distributing that thing. That's going to give us positive x squared minus 36x minus 1/2 times, let's just put a bracket there for now, but let's go ahead and FOIL this out. Negative x plus 36 times negative x plus 36. First, outer, inner, last. So x squared minus 36x minus 36x. That's minus 72, right? I gotta double check that because one little mistake and you're in the hole. Okay, and then that was 1296, right? Yeah. Okay. Okay, cool. All right, so let me just rewrite this. Because we haven't integrated with respect to x yet. I'm just trying to clean it up first before we do it. So we get negative 36x plus 1296 x squared minus 36x minus 1/2 times what we just found, which was that. X squared minus 72x plus 1296. Cool. Okay, so let's go ahead and distribute. So we have minus 1/2 x squared plus half of 72 is 36, right? Yeah. Okay, so that's plus 36x, half of 1296. Let's see. Sometimes it's just better to be safe than sorry. Let's see. Yep, there we go. All right. Let's go ahead and combine like terms. And hopefully I didn't mess this up somewhere. We're all going to hope for that. Okay, so 1296. Okay. These clear, that's cool. Okay, so this is minus 36x. Oh, there we go again with the donuts. Minus 648. Okay. right, excellent. So now that that's out of the way, let's go ahead and do this with respect to x finally. So we're going from 0 to 36. And let's integrate this. Oh, I could have combined these, huh? Let's do that. Okay, so this is 1295 over 2. Yeah, okay. Yeah, fine. Alright, let's go ahead and put that there. And I still haven't done this yet. I still haven't integrated it. Let's do it now that everything's combined. Okay, so this is going to be 1295 over 2x minus 36x squared over 2. And we're going from x equals 0 to x equals 36. And let's see. So the 0's not going to really matter, but let's see. 1295 times 36 divided by 2. So that's going to give us 23310 minus, okay, so we have 36 squared times negative 36, all divided by 2, minus 23328. Okay, negative 18 is our answer here. Alright guys, so I looked at my answer key, and this in fact is the correct answer, not this. So there was some kind of computational error in my calculations, but this is exactly how you should evaluate that integral. You know, the bounds didn't change or anything, but I made some sort of computational mistake somewhere along the way. But anyway, your correct answer should be 7,776 for that one. Alright, let's take a look at this one. We want to write a triple integral that gives a volume under the sphere, x squared plus y squared plus z squared equals 162, and above the region between y equals x and y equals 2x minus 9 in the xy plane in the first quadrant. Okay, so let's go ahead and set up our integrals. And again, I'm going to do z first just because it seems like that's the most complicated one. Now it tells us that we're going to be in the first quadrant here. And it's going to be, so in the xy plane, it's going to be bounded by the xy plane and the sphere right here. So for the xy plane, z is going to be 0. So we're going to start at z equals 0. And we're going to go all the way up until, you know, we have to solve this guy for z. So we have x squared plus y squared plus z squared equals 162. Let's go ahead and isolate z squared. So we got z squared equals 162 minus x squared minus y squared. Taking the square root, we get z is equal to the square root of 162 minus x squared minus y squared. All right. So that is going to be our upper bound here. So that's my z. So we have 1 because we don't have a function given to us to integrate. And we have dz on the outside. So what about our y and our x? Well, let's go ahead and sketch what our region looks like. So we're being told that the region is between y equals x. So let me go ahead and sketch this little region here. We got x here, we got y here, and y equals x is just a line through the origin with slope 1. So something like that. There's y equals x. And then y equals 2x minus 9 is going to have a y-intercept of negative 9, so maybe right here. And it's going to have a slope of 2, so it's going to be slightly steeper. And these guys are going to meet somewhere in quadrant 1, which is what we're looking at right here. Okay, so we're looking at this region. This is the region we're concerned with because it's in quadrant 1 and it's bounded by those 2 lines. Okay, so let's go ahead and figure out what our x and our y values are going to be. Well, let's see. In the x direction, if I start here at the leftmost x direction, well, I'm bounded by this guy right here. Right? So, because these lines are both, they both have a positive slope. Oops, sorry about that. We can say that, x is bounded to the left by this line, and x is bounded to the right by this line. Right? So we can set up our x's first. That might be a little bit easier. So, so in the x direction, well, let's see. This line to the left is x equals y. So if we're integrating with respect to x, so we have x equals y is our leftmost bound, and our rightmost bound is going to be this guy right here, and this is the line y equals 2x minus 9. So I have x equals, well, I need to go ahead and get this in terms of x, so I'll add 9 to both sides first, and then I'll divide both sides by 2 to get x equals y plus 9 over 2. So that's my rightmost x bound. This is y plus 9 over 2. And then for my y, so I did this with respect to x. Again, it doesn't matter what your order of integration is. I just thought it looked easier to look at it horizontally instead of vertically. And now my y is the last one here, and that can be a constant, right? We can, we can talk about constants here. Since we already took care of this as a function, we can now integrate with respect to y. So my lower bound, since I'm just in quadrant 1, my lower bound for y is going to be y equals 0, and my upper bound for y is going to be where these guys intersect. And where those guys intersect is 9, right? Because if I take well, let's see. I have y equals x, and I have y equals 2x minus 9. And so I have x is equal to 2x minus 9. So x is equal to 9, and therefore y is equal to 9. So I'm going from y equals 0 all the way up here to y equals 9. Okay, and it didn't ask me to evaluate this triple integral. The hard part is to just write the bounds down. So yeah, those are my bounds. We did z first, followed by x, and then followed by y after that. Alright, so let's do another one here. We want to find the volume of the region bounded by z equals x plus y. X varies from 0 to 7, and y varies from 0 to 7, and the planes x equals 0, y equals 0, and z equals 0. Okay, so this one's not too bad. Let's go ahead and set up our integrals here. So I like to do z first, and we're not given a function, so it's just 1. So we'll do dz, dy, dx. As this one is pretty straightforward. Alright, so my lower bound for z, we have z equals 0, and then my upper bound for z is a function. Z is equal to x plus y. And I'm wondering, did we do this one before? Did we do this one? Let's see. feel like we did one really similar. I just want to check this to make sure we're not redoing something we already did. Let's see. Okay, well, we did one like this, so yeah, I guess I'm gonna just skip over this one since we did one pretty similar. Alright, let's go ahead. But if you want to do this for extra practice, the answer you should get is 343. Okay, let's try this one. So we want to evaluate this triple integral. So now we have a function z. Okay, it's not 1. Where E is the solid tetrahedron bounded by the 4 planes and x plus y plus z equals 1. So this surface and these 3 planes as well. So let's go ahead and, we don't have to really sketch anything quite yet, but let's kind of, figure out where our bounds are going to be. Okay, so I know I have this, and this. I have z. Okay. I'm going to go ahead and look at this in terms of z, right? Because it looks like we can isolate z, and just to stay consistent with what we've been doing, we'll do this with respect to z first. So the lower bound on z is z equals 0. And if I isolate this equation for z, I get z is equal to negative x minus y plus 1. Okay, so that's my upper bound here. Alright, so we have dz Okay, so what about y? So we took care of z. Now what about y? Well, if I consider the xy plane, alright, so this is my y, this is my x. So z is equal to 0, so if I put z equals 0 in here, I get x plus y plus 0 equals 1. And then if I solve for y to make it look like a line, or to put it in like the form of a line, I get y equals negative x plus 1. Okay, so so that's going to be my my upper bound for, my upper bound for y. So I start at y equals 0, which is this line right here. X equals 0 is this guy right here. So it's bounded by those. And it's also bounded by y equals negative x plus 1. So if I plot this line that has a y-intercept of 1 and a slope of negative 1, so when I draw this, it's going to slope down like that. And so my region is just going to be in this little triangle right here. Okay, so let's go ahead and figure out what my my intervals are going to be, or my bounds rather. So here's my line, y equals negative x plus 1. And, below I'm bounded by y equals 0. And the bound above in the y direction is y equals negative x plus 1. So I could do y next. That would be kind of an easy thing to do because we're in a different situation where, this situation we had these two slanted lines and it wasn't easy to see what y was or what the bounds of y would be. But here it's a little bit easier because we have this horizontal line down here that's our lower bound, and this is our upper bound in the y direction. Okay, so we're going from y equals 0 to y equals negative x plus 1, and maybe I should have put this as equal to z. And then for the x, you can just do your constants since it's the last one. So we have dy, and then finally dx. Well, we're starting at x equals 0. And we're ending right here at this intercept. Well, what is this x value? That's when y equals 0. So when y equals 0, we have 0 equals negative x plus 1. Solve for x to get x equals 1. So that's from that is from x equals 0 to x equals 1. So now that we have all of this set up, that's always the hard part, is just setting it up. Now we can go ahead and integrate this thing. So we're integrating z with respect to z first. So that's going to be z squared over 2, and we're going from z equals 0 to z equals this mess, negative x minus y plus 1. Okay, so that's just going to be negative x minus y plus 1 squared over 2 minus 0. Yeah, let me go ahead and distribute this out so we don't make mistakes later on. Okay, so let's see. Negative x times negative x is x squared. Negative x times negative y is positive xy. Negative x times positive 1 is negative x. Then the y, positive xy, positive y squared, minus y. And then the last one is 1. So minus x, minus y, positive 1. Okay, do I have any like terms? Let's see. So I have x squared, and then these two can be combined to be 2xy. These can be combined to be negative 2x. These can be combined to be negative 2y. And then positive 1, positive y squared. And this is all over 2. So that's over 2. This is just going to clear to xy. This is going to clear to negative x when we divide by 2. This is going to clear to negative y. Plus 1/2 plus y over 2. Okay. So that's that. Okay, so now I want to integrate this with respect to y. So I'm going from 0 to negative x plus 1. Okay, so let's go ahead and integrate this with respect to y. So x is a constant, so this is going to be x squared over 2 times y plus xy squared over 2 minus xy minus y squared over 2 plus y cubed over 6 plus a half y. And we're going from y equals 0 to y equals negative x plus 1. Okay. Alright, so the 0 stuff is going to clear. Let's see, I'm looking for tricks that I can use to not have to do all of this. Let's see. Okay. So, yeah, I'm not really sure what we should do here, but just, let's see. No, I guess we'll just have to plug away. Okay, so plugging in for y, we get x squared over 2 times negative x plus 1 plus x times negative x plus 1 squared all over 2 minus x times negative x plus 1 minus, to make room, negative x plus 1 squared over 2 plus y cubed, so that's negative x plus 1 cubed over 6 plus 1/2 y. Okay, so I am not going to do all of this. Like, I'm not going to do the computation, but you should get something when you do this, and then you're going to integrate from x equals 0 to x equals 1. So we're going to go from x equals 0 to x equals 1, stuff dx, right? Whenever you simplify this, whatever you get. And I'm getting that your answer should be 1 over 24. Okay, and that is that one. Okay, so let's find the volume of the solid enclosed by the cylinder y equals x squared and the planes z equals 0 and y plus z is equal to 1. Okay, so let's go ahead and set up our triple integral. And we are not given a function here, so we're assuming that it's 1. So based on what we have, we can see that z is bounded below by 0, right? So z is equal to 0 is our lower bound. And if we go ahead and solve this thing in terms of z, we get that z is equal to 1 minus y. So that is going to be our upper bound there. All right, so we'll do with respect to z first. Okay, so now we can do it with respect to y. And what I can do here is I have y equals x squared, right? So I have y equals x squared. So here's my xy plane. So y equals x squared is parabola looking something like that. And also z is equal to 0. So if I plug in 0 here, I get y plus 0 equals 1. So y equals 1 is going to be my upper bound here. Alright, so I have these points right here. Alright, so for y, it looks like I'm bounded below by the curve y equals x squared. That's this parabola here. Right, that's my height from below. And my height from above is going to be y equals 1. So my height from below is y equals x squared. My height above, bounded above, is going to be y equals 1. Alright, what about x? What is my leftmost x value to my leftmost, or sorry, to my rightmost x value? Well, here we can see that this guy is going to be our leftmost x value, and this guy is going to be our rightmost x value. Right? And these are constants because I already took care of the function here. Okay, so what are those x values? Well, we just say, okay, well, we have y equals 1, we have y equals x squared. Let's see what these intersections are. So I set these two things equal to each other and solve for x. So if I take the square root of both sides, I get x is equal to plus or minus 1. So this guy is going to be x equals negative 1. This guy is going to be x equals positive 1. So we're going from x equals negative 1 to x equals positive 1. Now let's go ahead and integrate this thing. So we're going with respect to z, then with respect to y, then with respect to x. Okay, so with respect to z, this thing integrated is just z, and we're going from z equals 0 to z equals 1 minus y. Okay, so that's just going to be 1 minus y. Alright, and I'm going to integrate from y equals x squared to y equals 1, and then from x equals -1 to x equals 1. dy dx. Alright, so now integrating with respect to y, this becomes y minus y squared over 2, and we're going from x squared to 1. Okay, so plugging in for y, we get 1 minus 1 squared over 2 minus x squared minus x squared squared over 2. And we can clean this up a little bit. So 1 minus a half is a half minus x squared plus x to the 4th over 2. Okay. And okay, so that's done for y. Now I want to integrate with this with respect to x from -1 to +1. Okay, so with respect to x, this becomes 1/2 x minus x cubed over 3 plus x to the 5th over 2 times 5 is 10. And that's from x equals -1 to x equals 1. Okay, so plugging in 1 first, we get a half minus a third plus a tenth minus, now plug in -1. So that's going to be negative a half, positive a third, negative a tenth. And let's go ahead and compute this. Okay, so this is 4 over 15 minus okay, so this is going to be 8 over 15, and that is our answer. Alright, let's try this one. So evaluate the triple integral. So here we have a function 6xy, so that's actually a 3D surface. We can visualize this if we want to. And it says E lies under the plane z equals 1 plus x plus y, and above the region in the xy plane bounded by the curves y equals square root of x, y equals 0, and x equals 1. Alright, so let's go ahead and figure out our bounds and set up our triple integral. So this time our function is not 1, but it's 6xy. And this dv is going to be replaced by the little change in z times the little change in y times the little change in x. So for z, it looks like my lower bound, because it's above the region in the xy plane, so the xy plane means z is equal to 0. So we're going from z equals 0 to z equals 1 plus x plus y. So that's our z. So this is going to be dz. And then for y, we can sketch, for the xy plane, we can sketch all of this stuff just to get an idea of what this is going to look like. Above the region, the xy plane, bounded by y equals radical x, y equals 0, and x equals 1. So here's x equals 1. Here is y equals 0. That's y equals 0. And then y equals square root of x is going to be, let's see. Well, if I plug in 0 for x, I get 0 for y. Yeah, so it's going to look something like that. This is y equals square root of x. All right, so this is our region that we're concerned with right here. So if I want to talk about this in terms of height, in terms of y value, well, we can say I'm going to start at y equals 0, and the height that I'm at is going to depend on this curve. So it's bounded above by y equals square root of x, and it's bounded below by y equals 0. So y equals square root of x, that's on top. And then for my x values, I'm going to start here, right? I'm going to start here at x equals 0. And then right here, I'm going to end at x equals 1. That's where the curve is going to intersect that right bound. So we're going from x equals 0 to x equals 1. And now we can go ahead and figure out what this integral is. So we're going dz, dy, dx. Okay, so with respect to z first, this is just one big constant because there's no z involved. So this is just going to be, when I integrate it with respect to z, it's going to be 6xyz. And we're going from z equals 0, which is just going to clear, z equals 1 plus x plus y. Okay, so this is going to be, when I plug in the z, it's going to be 6xy times 1 plus x plus y. And I might as well distribute this. This is going to be 6xy plus 6x squared y plus 6xy squared. And now I can put my bounds back in. Y equals 0 to y equals square root of x. And then x equals 0 to x equals 1. And this is going to be dy first, followed by dx. All right, let's integrate with respect to y. So this is going to become 6xy squared over 2 plus 6x squared y squared over 2 plus 6xy cubed over 3. And we're going from y equals 0 to y equals square root of x. I'm going to clean this up before I put my bounds in. This clears to 3, so let me rewrite this as 3xy squared. This also clears to 3 right here, so that's going to be 3x squared y squared. This clears to 2xy cubed. Now I can put in my bounds. Be a little bit neater. Okay. Alright, so y equals root x. So we have 3x radical x squared plus 3x squared radical x squared plus 2x radical x cubed. And then minus 0, that's all going to go to 0, so I don't have to worry about that, which is nice. Alright, let's clean it up. So 3x radical x squared is just x, so that's 3x times x, plus 3x squared, again, radical x squared is just x, plus 2x, so radical x squared is x, so this is going to be times x times radical x. Right, because radical x squared is just x, so we have x times the leftover radical x. All right, so this is 3x squared plus 3x cubed plus 2x squared times x to the 1/2. That's radical x is x to the 1/2. So using the power rule, I can keep this x and add the exponents, right? So this is just 2x, so 2 plus 1/2. Well, 2 is 4 halves, so 4 halves plus 1/2 is 5 halves. So that becomes 2x to the 5 halves. So I'm just trying to make this look a little bit nicer before I finally integrate with respect to x. Okay, so this is plus 2x to the 5/2. I'm integrating with respect to x, and I'm going from, what was it, x equals 0 to x equals 1. Okay, so finally, let's go ahead and do this. So we have 3, I guess I can't scroll down anymore, 3x cubed over 3 plus 3x to the 4 over 4 plus 2, let's see, 5/2 plus 1 is 7/2, so 2x to the 7/2 over 7/2, which is just times 2 over 7, which is, so 2 times 2 over 7 is 4 over 7, so I'll change that to 4 over 7, just to make it look a little bit neater. Okay, and we're going from 0 to 1. So it looks like that clears to 1. X cubed. Okay, so I'm going to have to write this up here because I'm out of room. So I have x cubed, so that's 1 cubed plus 3 times 1 to the 4 over 4 plus 4 over 7 times 1 to the 7/2. Okay, so this is where I'm at. Okay, so basically I have 1 plus 3/4 plus 4/7. Let's see what that gives us. Plus 4/7. And I'm getting 65 over 28, which does agree with my answer key. Alright guys, that is it for this video. Thanks for watching. I hope these examples were helpful for y'all. And I'll see you guys next time.